So good evening, everyone, and I welcome you all to today's live session for the course Elements of Mechanical Vibration, NOC25-ae17. We are into the week 10 live session for this course, and yeah, so we are into the week 10 live session for this course, and we have already completed 9 live sessions where we have discussed about how do we deal with mechanical vibrations, how do we find out an electrical solution, or how do we actually deal with it, and what happens to the system when the system is damped, what happens to the system when the system is undamped. Then we extended this whole discussion to 2 degree of freedom systems, and we discussed about modal analysis. We discussed about multiple numbers of the existence of multiple numbers of natural frequencies, and etc etc. Now we are basically focusing upon multi-degree of freedom system. See, for 2 degree of freedom system, it is easy, right? It is easy for solving the equation because there are two equations, two differential equations, and we can easily solve it. But when we talk about multi-degree of freedom system, for example, we even talk about 3 degrees of freedom system, then what happens? The complexity of the problem increases. Though the equation is linear, the system is linear, but the complexity increases. Reason being that when we talk about complexity, if there are more number, like even for linear equations, if we try to solve it, if there are more number of linear equations, it becomes difficult for us to solve. Similarly, if there is multiple number of differential equations, it becomes difficult to solve each equation and find the correct solution. So that is why this discussion is all about how do we deal with the multi-degree of freedom system. In the last session also I discussed about that when we deal with multiple degrees of freedom, we actually try to write the equation in the form of matrix that helps us in generalizing the equations, and then we solve it using the matrix manipulations that we know to find out the solution. Like we also calculated the natural frequency of a system through the matrix approach, right? Now, similar to that, I have taken this question wherein we have to find out the natural frequencies and mode shape of the following system. See, last live session, I discussed somewhat a problem which was related to a 3 degree of freedom system, wherein we found out the natural frequencies. But there we discussed about a different kind of approach. I'm trying to summarize this in a different approach in this question. You are free to use whichever is convenient for you, but I prefer this method more over the initial method that I discussed in the previous live session, because I find this much easier conceptually and solving also, because we don't have to actually find the inverse of the matrix. Last time what we did was we found out the inverse of a matrix. We had a matrix D, and then we calculated the matrix, and then from there we calculated the natural frequencies. This time we don't have to find out the inverse. Okay, so how are we going to deal with it? Firstly, how are we going to write the sorry equation? The equation is going to be M is going to be a matrix, and then X is also going to be a array, which is going to be X double dot K X is equal to 0. After that, for this equation, we know that there is going to be a solution. Anyways, for the matrix M, we have M1 0 0 0 M2 0 0 0 M3. Hello? Hello? And we have K matrix as K1 minus K2 minus
इसको ये
K2.
सेटिंग और नहीं
Sorry, are you saying something? Your mic is on. Zero minus K3 minus K3 and K3. And here it is going to be 0. So these are going to be the mass and stiffness matrix. Anyways, the solution is going to be written as x a cos omega t, where x is definitely going to be an array because it's a 3 degree of freedom system. Similarly, we can evaluate x double dot by simply differentiating x with respect to time. This will give minus, because the differentiation of cos is sine, and then the differentiation of sine is minus cos, so it is going to be minus omega square a into cos of omega t. Okay, I hope this is clear. Now, if you put these both in this equation, okay, so then what are we going to get? We'll get m, which is going to be multiplied with, see, a cos omega t we can write as capital X, okay, so minus omega square m x plus k x is equal to 0. This implies k minus omega square m into x is going to be equal to 0. Now x cannot be equal to 0, because if x is equal to 0, it means that the system is not vibrating, but we are discussing about how the system is going to vibrate. So definitely x cannot be equal to 0. So the best way is that we evaluate the determinant of this and make it equal to 0. Okay. Now when we put the values of the K matrix and the M matrix, you get K1 minus M1 omega square minus K2 0 minus K2 K1 plus K2 minus M2 omega square minus K3 minus K3 K3 minus M3 omega square 0. Determinant of this is going to be equal to 0. Okay. Now, when we are going to solve this equation, what is going to happen? We are going to get, definitely, because there is a power of omega square and then we have a 3 cross 3 matrix, we are going to get a polynomial which has a power of omega to the power 6. Okay. So after doing all the calculation, I'll write the final equation. It is going to be m cube omega to the power 6 minus 4 m square k omega to the power 4 plus 3 m k square omega square is equal to 0. So if we assume, let lambda is equal to omega square, then what happens? M cube lambda square minus 4 m square k lambda. Okay, this is going to be a cube, this is going to be a square, plus 3 m k square lambda is going to be equal to 0. Now, this is a third order polynomial and we need to find out the roots. The thing is that definitely we have a lambda common, so one of the roots is going to be 0. So if we write it in that form, we take lambda common, m cube lambda square minus 3 m square k, or maybe we can take m as well as common, right? M m square 3mk lambda minus mk lambda plus 3k is equal to 0. Now from here, lambda 1 is equal to 0. So omega 1 is going to be equal to 0. From here, what do we get? Taking common m and lambda, m lambda minus 3k minus k m lambda minus 3k. Okay, we over here we have a k square equal to 0. So m lambda minus k, m lambda minus 3k. So then lambda 2 k by m, lambda 3 3k by m. So these are going to be the three roots that we are going to get from this equation. Corresponding to this, we are going to get three frequencies, right? Three natural frequencies, among which one is omega 1 is equal to 0, which means if I take out the eigenvector for this, it will turn out to be 1, 1, 1. Now this means that our system behaves like a rigid body, which means if I displace mass m1 by some amount, mass m2 and m3, all the three masses by the same amount in the same direction, it is not going to cause any vibration because spring will not come out into effect. See, spring effect is only going to come over here when there is some sort of compression or elongation of the spring. But if it displays all the three masses by the same amount, there is no compression, neither any elongation in the spring, right? So there is no motion that is happening, like vibrational motion, not motion actually. So the system is going to behave like a rigid body. So if I try to draw the mode shape, it will be something like 1, 2, 3. Mass m1, m2, m3, and this is x. It is all the three are going to have same amount of displacement. Let us say a. Then the omega is going to be 0. Okay, this is the first mode. Coming on to the second mode, which is corresponding to lambda 2 is equals to k by m, or omega 2 is equals to under root of k by m. Sorry, under root of k by m. So what is going to happen for this? See, for this kind of system, we are having a finite frequency. Okay, unlike the previous case where the frequency was 0, we have a finite frequency. Now, corresponding to this finite frequency, we are going to get the eigenvector as one, 0, and minus 1. So now if I try to plot, so what this is trying to say is basically this mode shape, that if you displace mass m1 by some amount a and you displace mass m3 by some amount minus of a, then the center mass is not going to displace in the left or right side. Okay, only the first and third mass are going to show vibration, that too with a frequency of under root of k by m. So the mode shape is going to be something like and 0. A. Oh, sorry, it should be in the negative direction. This is also. So this is the second mode shape. Coming on to the third mode shape. under root of 3k by m. What is going to be the eigenvector? It will turn out to be 1 minus 2, 1. So if now we try to plot it, it will be a minus 2, mass m1, m3, m2. This is the third mode shape. So last time what we did was we found out the D matrix, we did an inversion of a matrix, and then we found out the natural frequency. But here we didn't need to do that, because what we did was we did a manipulation like this, and then we had a simple matrix like this, and we just had to solve the characteristic equation, okay, in order to find out the natural frequency. Apart from that, this is a simple equation, and we had a free system, unconstrained system. Unconstrained means there was no constraint in the horizontal direction for the system. So because of which one of the frequency was 0, and the equation seemed easy, but it would have been a third order polynomial with none of the root equal to 0. It becomes difficult to find the roots. So in that case, you can use some kind of algebraic tool, like for example, you can use MATLAB or Maple. Those kind of softwares you can use in order to evaluate the roots of the equation. Anyways, coming on to question number 2. Find the free vibration response of the system shown below. Assume all masses of mass m and springs of stiffness k. All initial conditions are 0 which except here it should be x1, which is equal to x0. Okay. So we have this system. We have to assume firstly all the masses are equal to m, all the stiffness is equal to k, and then we have the initial condition x1 of 0 is x0. Apart from that, we have x2 of 0 is equals to x3 of 0 as 0, and x1 dot of 0 is equal to x2 dot of 0 is equal to x3 dot of 0 as okay. And we have to find out the free vibration response of the system. See, firstly, it's a 3 degree of freedom system. We have already done this kind of a question for a 2 degree of freedom system, and I hope that you people remember it. Now, since it's a 3 degree of freedom system, it is a bit complex because we will have to solve a total of 3 and 3, 6 equations with 3 and 3, 6. Yeah, definitely 6 variables of which value we don't know. So, anyways, we'll try to solve it. So first thing is that, as I told you earlier also when we were discussing the concept for a 2 degree of freedom system, that if we find out two independent solutions for a 2 degree of freedom system, then we can just utilize those two independent solutions, find a linear combination of those two in order to find out the general solution of the system. Correct? Similarly, for this 3 degree of freedom system also, the same thing applies. If we find three independent solutions for this kind of a system, we can write the general solution by the linear combination of those three independent solutions. So the first thing is to find those three independent solutions. As we discussed earlier, these independent solutions can be found out by the concepts of eigenvalues and eigenfrequencies, or by the concept of modes, modal frequencies, and mode shapes. Isn't it? That is how we did it, right? Similar is what we are going to do over here. We are going to first find the three natural frequencies, then we are going to find the three corresponding eigenvalues, and then using those eigenvalues and eigenfrequencies, we are going to find out the general solution. Definitely, we are going to write down the linear combination of these three as the solution, and then we are going to put time is equal to 0. We are going to get 6 equations. First, we'll get the solution, we'll get differentiated, we'll have two equations, sorry. In that, we'll put the initial conditions from which we are going to get a total of 6 equations. Corresponding to those 6 equations, we are going to solve for getting the values of the constants that we have assumed, and then we can write the general solution. So firstly, talking about the natural frequency. See, natural frequencies you can find out, but we did the same question of finding out the natural frequency of the same system in the last live session. So I'm not discussing about it. I'm directly going to write the frequencies and the corresponding mode shapes or eigenvectors. Okay. So the first one was omega 1, it was 0.0 0.44504 under root k by m, and the eigenvector is going to be 1, 1.8019, 2.2470. Second, omega 2, 1.2471 root k by m. One 0.4450 minus 0.8020. Omega 3 as omega 3 was, I guess, just a second. Let me see, I must have written it somewhere. Yeah, 1.805 the root k by m, and the corresponding eigenvector was 1 minus 1.2468, 0.5544. So these are the three frequencies and the corresponding eigenvector. Okay, and these we are going to use in order to find out the general solution. So for a 3 degree of freedom system, we can write the general solution in a generalized form, in the form of summation as x of t as summation I 1 to 3 x of I ai cos of omega it plus phi I x of 0 as summation I 1 to 3 x I ai cos of phi I. This is a general solution, and this is for initial condition, which is time is equal to 0. Okay, so definitely we are going to use it. Apart from that, we are also going to use the velocity term, right, to find out the equations, because then here we have basically 6 variables that we have to find out the value of. Xi we know, we need to find out ai and phi i's, which is going to be 6. So definitely we are going to use the velocity term as well, which is going to come out as xi omega I ai cos of phi. Both are for initial conditions. Okay. Now, when we put the initial conditions in this, what are we going to get? We are going to get 6 equations, which I'm going to write over here. A1 cos of phi 1 plus A2 cos of phi 2 plus A3 cos of phi 3 is going to be x naught, which is given in the question. Then we have 1.8019 a1 cos phi 1 plus a2 0.4450 cos phi 2 plus 0.5544 a3 cos phi 3 is equal to 0, and 2.2470 just a second. Yeah, 2.2470 a1 cos phi 1 minus 0.8020 a2 cos phi 2 minus 1.8025 a3 cos phi 3 is equal to 0. These are for the initial displacements. Similarly, we are going to find the three equations which we are going to derive for the three velocity conditions. So those are going to be minus 0.44504 under root of k by m a1 sine phi 1 minus 1.2471 under root k by m a2 sine phi 2 plus, not plus, it should be a minus only. The plus will come in the next equation actually. Not even next to next, a plus is going to come. Anyways, minus 1.8025 under root k by m a3 sine phi 3. So this was the first equation. Second equation, 0.80192 under root k by m a1 sine phi 1 minus 0.55496 under root k by m a2 sine phi 2 minus plus 2.2414 a3 sine phi 3 is equal to 0. And the third and the last equation is going to be minus of k by m a1 sine phi 1 plus under root k by m a2 sine phi 2 minus under root of k by m a3 sine phi 3 is equal to 0. These are for the velocity initial conditions. So in total, we are going to have three phase angles that we need to find out and three amplitudes to find out. A total of 6 variables that we need to find out in order to get the general solution. Correct? Now, solving these, we are going to get the values. Anyways, I'm not getting into solving, sorry. Anyways, I'm not getting into solving every of the equation. So our main aim is to find the value of, solve the previous equations and find the values of the variables. So these are the values that we need to find out. Now, if you will do it, I'm not getting into doing that because it's pure mathematical, there's no point. So we are going to get the values as A1 0.1076 x naught, A2 0.5431 x naught a3, 0.3493 x naught, and phi 1, phi 2, phi 3 are going to be equal to 0. This is anyways, this phi 1, phi 2, phi 3 you can see from here also actually. See over here, if you see for these last three equations, we have all the three equations equal to 0. Okay, so best probable thing is either a1, a2, a3 are 0 or phi 1, phi 2, phi 3 are 0, because everything is going to 0 every time. If it would have been 0 for one equation and the other two were going to have some values, then it would have been easy for us, because then we would have some values of phi 1 and phi 2, or phi 2, phi 3, any can have the value. But in this case, all the three equations which has a total of 9 different constants that it is multiplied with, still it is giving 0. It means either a1, a2, a3 are 0 or phi 1, phi 2, phi 3 are 0. Correct? So definitely phi 1, phi 2 and phi 3 are going to be equal to 0, because a1, a2, a3 cannot be equal to 0. And that you can see from the first equation as well. So that is what the solutions we are going to get. These are the values of the variables. And just a second. So these are the values that we are going to get. And now we can write the general solution, right? Now we have a1, a2, a3, and phi 1, phi 2, phi 3. So we can write the general solutions of x1, x2, and x3 as x1 is going to be x naught 0.1076 cos of 0.44504 under root k by m t plus 0.5431 cos of 1.2471 under root k by m of t plus 0.3493 cos of 1.8025 under root k by m of t. This is the solution for x1. For x2 of t, we get the solution as, for x2 of t, we get the solution as x naught 0.1939 cos of 0.44504 under root k by m of t plus 0.2417 cos of 1.2471 under root k by m of t with a minus 0.4355 cos of 1.8025 under root k by m of t. This is the solution for x2, second solution. And the third one is going to be x3 of t x naught 0.2418 cos of 0.44504 under root k by m of t minus 0.4356 cos of 1.2471 under root of k by m into t plus 0.1937 cos of 1.8025. So these are the solutions of x1, x2, and x3. Now if you look clearly over x1, x2, and x3, these are nothing but a linear combination of, these are nothing but the linear combination of three independent solutions, which we assumed as like this, right? Nothing but a linear combination of the three independent solutions. That is what I was telling. If we have three independent solutions, we can write any general solution by a linear combination of the three independent solutions that we have found out. Now we'll be working on question number 3. Using modal analysis, find the free vibration response of the 2 degree of freedom system with equation of soft motion this. Now in the previous case, what were we doing was we were finding three independent solutions, and then we were just writing a general form, and then we were finding out the constant values. But then there is a modal analysis which says that if I have a equation of motion which is coupled. Coupled means that the equation of x1 has variables x2 and the equation of x2 has variables x1. We can decouple the equation, and if we decouple the equation, we get a solution for x1, we get a solution for x2. Using that x1 and x2, we can find the solution. This is what modal analysis says. But for that, we first need to decouple the equation, right? So see, firstly, we have the equation which is given over here, right? So the first thing is definitely going to be to find out the natural frequencies. Anyways, modal analysis is also based on the concept of finding the general solution, and for that we definitely require the natural frequencies or the modal frequencies, right? Because on the basis of that only we are going to make our system decouple. Okay. So finding out the natural frequency, we have m x double dot plus k x is equal to 0. So in the previous case also what we did was we assumed x as a cos of omega t, correct? Using that, what do we get? K minus omega square m into x is equal to 0. Now x cannot be 0, so the determinant of k minus omega square m is going to be equal to 0. Okay. Using this, we can find out the natural frequencies, right? For this equation, we are going to get this as a form k1 plus k2 minus m1 omega square, k2 plus k3 minus m2 omega square, minus k2 minus k2. This is going to be equal to what? 0. This is going to be equal to 0. So from this, we are going to get omega 1 as 1.5811 and the corresponding x1 as this is the eigenvector, okay? Or the mode shape, you can say 2.4495 with x2 as so these are the two frequencies and mode shapes. Now we can write this in a general form, right? For example, for our system, we had this equation, right? This equation we had. This we can further write as by taking k on the other side or omega square on the other side. We can write it as omega square m x is equal to k x. We can write it like this, right? Where omega is what? These are the modal frequencies. Corresponding to them, we have mode shapes, which are These are what? Mode shapes. Okay, it's clear, right? Right? We have to solve that equation. Now, what we can do is we can assume the solution x of t as nothing but the multiplication of multi summation of the multiplication of, we have supposed that there is q1, q2, q3 and qn, which are the independent solutions, which are the decoupled solutions. Okay, and if we multiply it with the mode shapes, then we can assume the general solution as x of t, right? We can write this further in the matrix form as x into q of t, where q of t is nothing but q of t, you already know. Basically, x is going to be what? It is going to be a matrix that confines all the mode shapes. X is going to be, these are going to be the mode shapes. Okay. Now, okay. Now we have assumed x as a multiplication of capital X and Q of t. Now, in order to find out the general solution, we need to know capital X and Qt. Capital X we already know, but there are two constant values that we need to find out, and then Qt we have to find out the whole, right? So the first thing is that how do we find out Qt? Anyways, Q is known as modal perturbation coefficients. Okay, so how do we find out Qt? So now we try to manipulate our equation. How? See, we already have m x of t plus k x of t is equal to f. Correct. Now we have already assumed x, so we can replace it over here. So we get m x, it is going to be a double dot, q double dot plus k x q is going to be equal to f. Now what if we pre-multiply this whole equation with x transpose? With x transpose. X transpose k x q of t is equals to x transpose into f. Now, if you look over here, if we can just say that this is a generalized force vector, right? And we can see that this is nothing but an identity matrix. X of t into m into x is nothing but an identity matrix. And x of t, k, x is nothing but a diagonal matrix with its diagonal elements equal to omega square, where omega is what? is the natural frequency of the system. See, this sorry, this is because the mass matrix is the same and x is nothing but the, if you remember, x is nothing but the mode shapes, right? So if we pre and post multiply our mass matrix with the mode shape and its transpose, what is going to happen is that it is going to give us identity matrix. And same with stiffness is going to give us a diagonal matrix in which the diagonal elements are nothing but the frequency square. Okay. So now the equation becomes q double dot of t plus omega square q of t capital Q of t. Now, if you look closely to this, this is somewhat of the form qi of t double dot plus omega I square qi of t is equals to capital of q I of t. So this is like a single degree of freedom system, isn't it? Single degree of freedom, undamped and forced. And for this kind of a system, we know the solution. We know the solution, isn't it? We have already done many questions and we have discussed this theory many times till now, right? So for this, we know the solution, which is written in terms of the initial velocity and initial displacement, isn't it? So we can write it as for any general solution qi of t, we can write it as qi of 0, which is the value of q at time 0, cos of omega t plus q dot of 0 by omega I sine omega I of t plus 1 by omega I integration from 0 to t qi of t sine of omega I t minus tau d tau for I 1, 2. So this is the general solution. So now we know that what we have to do. X1 and x2 we have, but we need to find out the constants which are multiplied with it. Second, we have to find q1 and q2, and then we can calculate the solution. Anyways, this is easy because the third term in our case is going to be equal to 0 because as the case of free vibration. So by orthogonality, the mass term we get for x1 vector multiplied with m into x1 is what? 1, right? Identity matrix. So get x1 of 1 square into, what is the first vector? 1, 2. Then mass matrix, which is mass is 1 is 10 and other is 1. 10, 0, 0, 1, 1 and 2 is going to be equal to 1. Now if you will multiply it, what are you going to get? You'll get this multiplied is going to be 1, 10, and this multiplied is going to be 2, and then this whole multiplied with this is going to be 10 plus 2 to 4, 14, 1 divided by 14. So x1 of 1 is going to be under root of 14, which will give us a value of 0.267. Oh, sorry, I said wrong. Under root of 1 by 14. So this is the value of x1 of 1. Similarly, we can find out the value of x2 of 1 by orthogonalizing x2 m air transpose x2 1. Yeah, so we are going to get x2 of 1 as 0.1690. Okay, so now we can find out capital X, which is nothing but x of 1, x of 2, 0.2673, 0.1690, 0.5346 minus 0.8450. This is going to be the capital X matrix. Now coming on to the second thing that we have to find, which is small q1 and q2. So if you see, for us, we have qi double dot of t plus omega I square qi of t is equal to 0. So qi of t is nothing but q10 cos of omega I t plus q10 dot by omega I into sine of omega I t. This is going to be the general solution in our case, because the third term, which was related to forcing, will be 0 because we have no forcing over here. Okay, so this is going to be it. Anyways, q dot of 10 is 0 for both first and second mass, right? For the first and the second directions. So in that case, we can simply write q of 0 as q10, q20 at 0, right? This is what it is, because see over here, see, we need to find out q0, because then only we can write q1, isn't it? So now we can write this q1 of 0 as x transpose m x0. I think you get from where is this coming from. From where are we getting this? See, we had q written, right, over here. This equation we have, right? Now we have to find out q of 0, right? The vector at q0. Okay, just a second. I must have written the value somewhere. Where is that equation? Okay, now if you look over here, qi of t at time t is equals to 0, it will depend upon what? See, it will depend upon only the first term, correct? It will depend only on the first term from which we are going to get q of 0. Now, in order to find q of 0, we all know that we can write it in this form. So, there is how we are getting it. Okay. Now, if you put the matrix over here, if you put the matrix over here, we get q of 0 as 0.2673, 0.1690, 0.5346 minus 0.8450 into the mass matrix 10, 0, 0, 1, 1, 0, which is going to give 2 point, okay, I've written it, 673, 1.690. This is going to be q at 0, right? This is going to be the q at 0. Similarly, now, if we try to find out corresponding to the velocities, we are going to get q of 0 dot is nothing but q dot of 10 at 0, q dot of 20 at 0, which is nothing but x into m, x dot at 0. Anyways, x dot at 0 is what? 0, 0. So definitely this is going to be 0, 0. Okay, I hope this is clear. So now we have the value of constants. Now we have the value of constants. So definitely now we can write q1 as 2.673 cos of 1.5811 t and q2 of t as 1.690 cos of 2.4495 t, right? So now final equation which says that x of t is nothing but capital X into capital X into q. So we just have to put everything over here. 0.2673, 0.1690, 0.5346 minus 0.8450, 2.673 cos of 1.5811 t, 1.690 cos of 2.4495 t. This will give the solutions of x1 t as 0.7145 cos of 1.5811 t plus 0.2856 cos of 2.4495 t, and x2 of t is 1.4280 cos of 1.5811 of t not plus, it should be minus because there is a minus over here, minus 1.4280 cos of 2.4495. This is the main answer, which is the solution, the general solution. Anyways, did you see what we did over here? In the previous question, we had 6 equations which we had to solve and then find out. Overhead, it was easy for us. Though we had this equation to solve for this one, and this one. But for with matrix multiplication, it becomes easy. And then we just have to simply multiply capital X with Q of T vector in order to get the final solution. I hope this is clear. Okay. Now coming on to question number 4, which is like the previous question also we were using modal analysis. Here also we'll use modal analysis. The only difference is that previous was a case where we had no forcing present. Here we have sort of an impulse response, or we have a response which will act only for the initial 0.1 second. After that, it is not going to apply. Okay. So, yes. See, what do we have? We have the force acting on the workpiece of the forging hammer shown below due to impact by the hammer and can be approximated as a rectangular pulse as shown. Yeah, this is the rectangular pulse. Okay, and we have a 2 degree of freedom system, something like this. And we have force which is acting on only mass m1. Okay, we have force which is acting only on mass m1, and this m1 mass is getting the force, m2 is getting no force. Okay, so we have to definitely find the resulting vibration of the system for the following data. We have mass of the workpiece, anvil and frame as 200 capital mg, which is megagrams. Then mass of the foundation block as 250 megagrams. Stiffness of the elastic pad K1 as 150 meganewton per meter. And stiffness of the soil, which is K2, as 75 meganewton per meter. And we have to assume initial displacements and initial velocities of the mass are 0. So we have okay. Apart from that, we have M1 as 200, M2 as 250, K1 as 150, K2 as 75. So definitely the first thing which we are going to work upon is finding the frequencies. So again, mod of K minus omega square n will be 0. This gives us this gives us 150 minus 150 minus 150, 250, not 250, 225, right? 150 and 75 square. 225 minus omega square, they have 200 and 250. This is going to be equal to 0, which gives omega square minus 150 minus 150, 225 minus 250, omega square is equal to 0. Okay, from this we get 150 minus 200 omega square, 225 minus 250 omega square not plus, it will be minus 225,000. From this, we are going to get omega 1 as 12.2474 radians per second and omega 2 as 36.7298 radians per second. Okay, so these are the frequencies. Now we have to find the corresponding mode shapes, which will turn out to be x of 1 as a 10.8 and x of 2 as b 1. These are the two mode shapes. Now, when we try to find out the solution, what do? First is we find out a and b by what? By orthogonalizing. So by x transpose into m into x is going to be I, which means x of 1 transpose m x of 1 is 1 and x of 2 transpose m x of 2 is 1. So this both is going to give the value of a as 1.6667 10 to the power minus 3 and b as 1.4907 10 to the power minus 3. So from this, what are we going to get? We are going to get the capital X. We already got capital X because now we know A and B. So we can finally write the equation of capital X as capital X. We can write as capital X as this, which will turn out to be 1.6667, 1.4907, 1.3334 and minus 1.4907 total multiplied with 10 to the power minus 3. I will not write x over here because then it will be the sign of multiplication, because then it will have a confusion. You can just understand that this is multiplication. Okay. Now, the main thing is finding out QI, right? Which in this case will not depend upon the initial condition, because definitely both the initial conditions are equal to 0. It will just depend upon the forcing. It will just depend upon the forcing, right? Just a second. See, look over here what we did in the previous question. See, if you look over here, see, this was because of initial displacement. This was because of initial velocity. Now for this question which we did over here, our initial velocity was 0. And this third one, which was because of external forcing, it was 0. So what we did while finding out Q, what we did was we considered only this one, right? And hence we used the equation which was Q for Q1 of 0. which is written as this x transpose mass into x of 0. Correct? But now we are more concerned about this term. So definitely we'll try to find out qi. We'll try to find out qi because small q depends on capital Q, and capital Q is given over here, which is x transpose into the forcing function, right? Which is x transpose into the forcing function. And that is how we are going to get the small qi over here. So small qi is going to be 1 by omega I, integration from 0 to t. For now, we are not considering that what kind of forcing is there and not. For now, we are just considering from 0 to t. And then we have q of I tau sine of omega I t minus tau t tau for I 1 comma 2, where qi time is given in terms of x transpose into f of t. Now x transpose we can find out. F of t we already know, right? So we can further write this as q1 of t and q2 of t as 1.6667, 1.3334, 1.4907 minus 1.4907, 10 to the power 3 into f1 of t and 0. Okay. This will be further written as 1.6667 f1 of t, 1.4907 f1 of t into 10 to the power minus 3. So now we can write the final solution x1 of t and x2 of t as capital X into q of t, capital X into q of t, which is 1.6667 q1 of t plus 1.4907 q2 of t and 1.3334 q1 of t minus 1.4907 q2 of t, wherein q1 of t is nothing but 3.4021 integration from 0 to t sine of 12.2474 t minus tau d tau, which is equal to 0.2778 1 minus cos of 12.2474 t, and then q2 of t is nothing but 0.9622 integration from 0 to t sine of 38.7298 t minus tau d tau, which is 0.02484 1 minus cos of 38.7298. Okay, this is the final answer. So coming on to question number 5, wherein we have to derive the equation of motion of this system. Now we have already done various, problems of finding out the equations of motion, but I thought of maybe considering this because I wanted to, just let you practice a question wherein there is a 3 degree of freedom system, and then we are supposed to find out the equation of motion. Now you see, in order to find out the equation of motion, we have several ways, right? we have, firstly, we have conservation of total energy, which is applicable only in the case of conservative system, right, which has no damping present over here. So that is not applicable over here. Second one is by force balance, which is fine, but it is sometimes complicated for us because we have to think about what force is acting in which direction. We have to make, like for here, we have three masses, so we'll have to make uh, three body diagrams, and then we have to sum up all the forces and everything in order to get the solution. Now, the best way for these kind of a multi-degree of freedom system, wherein it is a bit difficult or time consuming to find out the equation of motion using the force balance method, is to use the modified Lagrange equation. You know, the modified Lagrange equation is applicable on these kind of a system which has damping present over there. So what do we do in the modified Lagrange equation is that we find out the total energy first, which is the potential energy we'll find out, then we'll find out the kinetic energy. And then after that, we'll find out a Rayleigh dissipative potential, which is defined for systems which has damping present in it. And using the Lagrange equation, we can then find the equation by just differentiating. So it becomes easy, right? So for this kind of a question, first we need to find out the kinetic energy. Now, kinetic energy is the one which refers to be there inside the system because of the velocity present. So m1 is going to have a velocity of x1 dot of t, m2 is going to have a velocity of x2 dot, and m3 is going to have a velocity of x3. Now, this is a simple system. So we can simply write the kinetic energy as half m1 x1 dot square, half mv square, plus half m2 x2 dot square, plus half m3 x3 dot square. Okay. Similarly, we have to write what? The potential energy term. Now, potential energy is going to be because of the presence of the springs, right? So, potential energy, firstly, if we write for mass m1, you can see that there is a spring which is attached directly to the system, a spring which is attached directly to the system m1, correct? It is going to store the energy like half k1 x1 square because there is no relative displacement in k1. Okay, there is just absolute displacement. Now plus half. For k2, if you see, k2 links m1 and m2. So it will depend upon the relative displacement between m1 and m2. So this is going to be half k2 x2 minus x1 square. Okay. And now coming on to the third spring, which is attached in between m1 and m2 and m3. M2 and M3. Now, similar to the case of K2, K3 is going to depend upon the relative displacement between M2 and M3. So, the spring energy that will be stored, it will depend upon the relative displacement between M2 and M3, which can be written as half K3 x3 minus x2 square. Okay, I hope this is clear. This was very easy. Coming on to the dissipative potential. See the Lagrange equation. In the Lagrange equation, we define Lagrange as kinetic energy minus potential energy. And then we have the equation written in the form delta L divided by delta Qi dot minus delta L by delta Qi plus delta R by delta Qi dot is equal to 0, 0 because we have a unforced system. If there would have been a forced system, this 0 would have been replaced by Q. Okay, where I is nothing but 1, 2, 3. Okay, I'll write Q only over here for now. So this is what we want to have. So kinetic energy we have already evaluated, potential energy we have already evaluated. We have to just evaluate the third thing, which is the Rayleigh dissipative potential. Now the Rayleigh dissipative potential in general is defined as half C x dot square, similar to something like kinetic energy. But in this case, we have multiple springs. We have a total of 5 springs. So firstly talking about the first spring. I'm saying spring, I'm really sorry. It should be dashpot. The Rayleigh dissipative potential will depend upon the dashpot. So for the first dashpot C1, there's only absolute displacement x. So it will be half C1 x1 dot square plus for C2. If you look, we have the relative displacement, right? Because C2 connects M1 with M2. So definitely the relative displacement between M1 and M2 is going to give the value of the Rayleigh dissipative potential, right? So this is going to be half C2 x2 dot minus x1 dot square, okay, plus half. If you see C3, C3 connects M2 and M3, so it will depend upon the relative velocity between M2 and M3. So C3 x3 dot minus x2 dot square plus half C4. Now for C4, C4 is connecting the reference to M2. So technically C4 is just dependent upon the velocity of M2. Okay, it does not depend upon any kind of a relative term. So we'll have C4 x2 dot square. And the last one, which is half into C5. Now C5 connects M1 and M3. Okay, it is skipping M2 and connecting M3. So C5 will depend upon the relative displacement between the M3, sorry, not relative displacement, it should be relative velocity. So M3 and M1. M x3 dot minus x1 dot square. Okay. Putting the KE, PE, and R equations into the Lagrange equation, comma, gives the equation of motion in the form m x double dot plus c x dot plus k x is equal to 0, wherein when we find out the values, m is m1, m2, m3, 0, 0, 0, 0, 0, 0. Definitely it is going to be a 3 cross 3 matrix because it's a 3 degree of freedom system. C C2 plus C3 plus C4, C3 plus C5 minus C2 minus C2 minus C5 minus C5 minus C3 minus C3. And the last, which is the stiffness matrix, it will turn out to be K1 plus K2 minus K2 minus K2. I guess there is some network issue because I can see lag between what I'm writing and just a second. Okay, there's some network issue. Anyways, I'll continue now. Minus K2, K2 plus K3, 0, minus K3, K3, minus K3, and 0. And definitely X will be nothing but X1 of t, X2 of t, X3 of t. I skipped the like the differentiation and everything part because it is simple mathematics that you people can do on your own also. It would, if I would have been getting into that, it will just take uh, a lot of time. Now, find the steady state response of the system given in the previous question when all masses are subjected to harmonic force with omega this. Assume C4, C5 as 0 and all the masses are m and stiffness are k. Okay, so for the previous question we had three masses where we have to assume m1, m2 and m3 are equal to m. K1, K2 and K3 are equal to k. C4 and C5 are 0 and then the masses are subjected to F1, F2, F3 as F naught cos of omega t, where omega is 1.75 k by n. Okay, we need to find out the steady state response. See, up till now, when we were solving any question, we were mostly concerned about finding the free response of the system. And then we took a question where there was some kind of a impulse in the beginning. But this is about when damping is present in the system and then there is forcing. See, when the system is having a forcing, the vibration will have two components. One is because of the natural frequency. Second one will be because of the forcing frequency. Now, if the damping would have not been present, we would have to consider both. Since damping is present over here, after a certain time, the vibration, which is because of the natural frequency element, it will actually reduce with time. And in the steady state, the vibration which is there because of the forcing function will only be present. Okay, the one which is because of the natural frequency will just fade out with time because of the damping. Okay, so firstly, finding out the natural frequencies, I'll not go into it because now people are very much known about how to find it. So omega 1 is 0.44504 under root k by m, and the corresponding mode shape is x of 1 as 0.3280 by under root of m 1, 1.8019, 2.2470. Second mode, second frequency is 1.2471 under root of k by m, corresponding mode shape x of 2, 0.7370 by under root of m 1, 1.4450 minus 0.8020. And then we have omega 3 as 0.5911 under root of k by m. Okay, no, this will come 1.8025 actually. X of 3 is going to be 0.5911 by under root of m minus 1.2468, 0.5544. Okay, these are the three mode shapes and the three frequencies. Now, we have to find out the x vector, right? Because then we can write the solution by using the x and q. So for the x is nothing but x of 1, x of 2, x of 3 as 1 by under root of m 0.3280 0.5911, 0.7370, 0.7370, 0.5911, 0.3280, minus 0.5911, minus 0.7370, 0.3280. Okay, this is X. The next step is to calculate Q, right? Small q, again, it depends upon the initial displacement, initial velocity, and the force. Initial displacement and velocity we are not concerned about because it will fade out in the steady state. In the steady state, the response will be present only because of the forcing function. Okay, and that we write as q of t as x transpose into f of, which is nothing but 1 by under root of m into this vector into f naught cos of omega t, f naught cos of omega t, f naught cos of omega t. This can be written as q10, q20, q30 into cos of omega t. Okay, so after multiplying, you'll get the values of q1 of 0 as 1.6561, 1.6561 f naught by under root of m, q2 of 0 as 0.4739 f naught by under root of m, and q3 of 0 as 0.1821 f naught by under root of m. So these are q1 of 0, q2 of 0, and q3 of 0. Now for the damped case, the solution, firstly the decoupled equation is written in the form like this: q1 of t plus 2 eta I omega I q dot of it plus omega I square q of t is equals to q of it. Now, if you look over here closely, this is similar to the one we were doing about the undamped case, right? While for the undamped case, there was not the second term or the q dot term, which was that was not present over here. But over here we have the q dot term, and mainly the thing that should be kept in mind over here is that the modal analysis is built in the way such that it becomes easier for us to relate to the single degree of freedom system, right? We have basically taken 2 eta I omega I q I of t because it will help us to relate to the solution we were talking about in the single degree of freedom system. We had the spring mass Ashford system like this only, right? So now we know how to find out the steady state solution, isn't it? Because qi of t for this kind of a system is what? Q I of 0 cos of omega I t minus phi I. Correct? Where phi I is the phase angle and omega I is the ith natural frequency. So we have Q I of 0 written as capital Q I of 0 divided by omega I square into 1 divided by, first was 1 minus omega by omega I square. Omega is the forcing frequency. And omega I is the ith modal frequency. Okay, whole square, this whole square plus 2 eta I omega I divided by, no, I guess there was omega in the above here. Omega I whole square is whole to the power 1 by 2. Similarly, phi I, which was the phase angle, it can also be found out as tan inverse of 2 eta omega by omega I divided by 1 minus omega by omega I square. Now, when the values are put, this one, these things, when you put this in these equations, you'll get q1 of 0 as 0.57815 f naught m by k, q2 of 0 as 0.31429 f naught under root m by k, q3 of 0 as 0.92493 f naught under root m by k. Further, we need to find out the phase angles as well. And in this question, the phase angles are actually not equal to 0 because generally when we have a forcing function present in the system, there is some amount of phase angles, right? So the phase angle will turn out to be q1 as tan inverse of minus 0.00544. Phi 2 is tan inverse of 0.09288. Phi 3 is equal to tan inverse of 0.33827. Okay, so now we know what q vector, which is nothing but 0.57815 f naught under root m by k cos of first frequency was again 0.44, yeah, 0.44504 t minus tan inverse of 0.00544. Second one as 0.31429 f naught under root m by k cos of 1.2471 t minus tan inverse of 0.02988, and the third one is 0.92493 f naught under root m by k cos of 1.8, I guess 1.8025 t minus tan inverse of 0.33827. So this is the q vector, and we can write the solution x of t as x into q of t. This you people can do, it will take unnecessary time, I don't want to get it. Okay, so see, basically in this question, just a second. Okay, so basically in this question, what did we do? We had a system, so somewhat like this, only C4, C5 was equal to 0. And we had forcing that was happening on all the three masses, right? This was cosine. Although all the three forcing was same, but anyways, it was forcing that was happening. In the two questions that we did earlier, the first question was about undamped, unforced phase. We had a system. Sorry, we had a system wherein we had a 2 degree of freedom system and we were supposed to find out the solution. So firstly, we attempted to find out the solution in a general fashion, which we were doing earlier. Secondly, we tried solving the equation using the modal analysis, right? Wherein using the modal analysis, wherein what did we do? We found out the frequencies, modal frequencies. We found out the eigenvectors corresponding to that. Using that, we assumed that okay, my solution can be written as the multiplication of capital X, which was the which we were getting from the eigenvectors, and then Q, which we assume that is the solution for the uncoupled equation, right? We put it into the equation and then we got the ways of finding out how to get the Q, right? So Q was an equation which was somewhat similar to that of, not even somewhat similar, it was same as that of the single degree of freedom system, right? Single degree of freedom, undamped system. So we just evaluated capital X, wherein we had two constants. We used the concept of orthogonalization to find out the values of those two constants. And then we used the equation of some, like mx double dot plus kx dot to find out the solution. Now for that solution, the solution was based on three things. First one was the displacement, initial displacement. Second one was because of the initial velocity. And third one was because of the forcing. So for the first question, we had only the initial displacement, no initial velocity and no forcing. So only the first term was there, which was responsible for finding out the solution. We found out the value of Q. For the second question, what we did was now the initial conditions of the displacement and velocities both were equal to 0, and the response was there because of the forcing function. But it was an undamped case. Right? So the solution was dependent upon what? Whatever the frequencies that we calculated. Yes, right. Whatever the frequency that we calculated. Right? Now, what is important over here is to note that this is a damped case. Right? This is a damped case. So here, the contribution of natural frequencies is going to be 0. Why? Because the natural frequencies are going to be there in the transition phase. The transient vibration are going to have the response, which is because of the natural frequencies. In the steady state response, every transient amplitude and everything is going to damp out with time. And the steady state response is just giving in of the energy because of the forcing, and excessive energy is getting out because of the damping, and the system is going to vibrate only at the frequency omega. So over here, what I did was the frequency that I have written, it is not correct, isn't it? That is why I wrote the wrong frequency so that it becomes easier to point out. This will not come over, but rather the forcing frequency is going to be there, isn't it? The forcing frequency is going to be there, which is 1.75 under root of k by n. 1.75 under root of k by m, 1.75 under root of k by n. What is important over here is to note that when we are talking about mode shapes and then we are talking about the modal frequencies, this is going to play the role only if my system is undamped. Once my system becomes damped and then a forcing is applied to it, there is no point of discussing about the modal frequencies, because every single mass of the system is going to oscillate with the forcing frequency only. If the system is damped and we are talking about steady state solution, see, it is definitely going to have the contribution of the natural frequencies when the system is in the transient phase. Right, in the transient phase, it is definitely going to have the contribution which is because of the natural frequencies or the modal frequencies. But once it crosses the transient phase, the transition occurs and it is now at the steady state solution. The contribution of only the damping frequency is going to be there, right? Over here also, the damping that we have considered and then we have solved, it is the proportional damping, right? Proportional damping means C is actually proportional to the mass matrix and then it is proportional to the stiffness matrix and then we add. This is a proportional damping, right? This is the proportional damping. But once, no, for the solution that I've given over here, it is because of the proportional damping. We have already considered that the damping is of the this form, okay, where alpha and beta are constants. But if the damping is not proportional, then what are we going to do? Well, then it becomes a complex case because in that case, as I've told you, the concept of mode shapes and the contribution of mode shapes and modal frequency that already has come out because of the damping present and the forcing. Damping is going to damp out the transient thing, contribution of the natural frequencies, and the forcing is going to impart the system in such the energy in such a way such that it is going to oscillate with a frequency which is equal to the forcing frequency. So there's no contribution of the modal frequency, right? So anyways, for this case also we have considered a proportional damping case. What if there is no proportional damping? Then it becomes a complex case, right? And then what is important over here is to note that if we are practically seeing any system, some kind of a damping is going to be there, right? Some kind of a damping because energy is never going to be constant. That is what thermodynamics says, right? Energy is going to degrade. Okay, with time, if you give something some initial energy, it is going to degrade because of air drag, because of damping, because of various reasons, right? So the energy is going to get dissipated because of various reasons, but it is going to dissipate. However, in the ideal world, it may happen that you cannot, but we are living in a non-ideal world, right? So when we are talking about a practical problem, what is the even the need of modal frequencies? First thing, never oscillate the system at the modal frequencies because at that time it can show resonance condition, right? We should avoid it. Second, that is what for modal analysis is needed. Second thing is that when we are talking about the system, like the structural system, wherein the mass and stiffness is very, very high as compared to the damping value. So over there, the concept of modal frequencies and modal shapes are very important, and the mode shapes becomes very important because if the damping is very small, the dissipation is going to happen, but it will take a very, very large amount of time, right? So for a very large amount of time, initially, if we look at some initial vibrations, it will seem that it is almost TV. So in that case, it is very important that we look into the modal shapes, mode shapes and everything so that we avoid any kind of a failure. Anyways, for a damped and a forced system, mostly the system response is going to be dependent upon the damped frequency only. So we should not be concerned much more on uh, modal frequency and anything. But then, in order to know the internal behavior of the system, it is important to know the natural frequency, and then the modal analysis is definitely important in order to find out the this modal frequencies or the natural frequencies, right? In order to so that if we know, then only we are going to avoid it. Okay. Okay. So we have 10 minutes more, and we have last problem. So this is a very easy problem. So we have for a 2 degree of freedom system, the natural frequencies are 5 radians per second and 15 radians per second. Okay, and we have to find out the modal damping ratios for the proportionality constant this. So firstly, for a 2 degree of freedom system, omega 1 is 5 radians per second, omega 2 is 15 radians per second. Okay, then we have proportional damping, which is alpha into m plus beta into k, and we already have the value of alpha as 0.02 and beta as 0.001. Okay, so what we basically do is we assume that our damping can be written as proportional values of mass and stiffness matrix. Okay. Anyways, this C is also going to be a vector. S- So because for n degree of freedom system, they are going to be n dampers, n dashpots, and they are going to have their own damping values. Okay. And it will depend upon definitely the mass and the stiffness of which is concerned with that particular element. Okay. Now there is this one equation which says that 2 omega I eta I is equals to alpha plus omega I square beta. This comes from a derivation which you can see in the book. I will not get into it because we don't have that much time. So this is the equation that we have. Now the question says this, find the modal damping ratios, which is eta i's for the proportionality constants alpha this and beta this. So we have this equation. We already have the values of omega I, which is omega 1 and omega 2. This is for I 1 comma 2. Okay. So this eta I is 1 by 2 alpha by omega I plus omega I into beta. Alpha and beta values we know. So for omega 1, which is 5 radians per second, right, we have eta I as 1 by 2 into 0.02 divided by 5 plus 5 into 0.001. This is going to be 1 by 2 and 5, 4, 0.004 plus 0.005, which is 0.009 by 2, which is 0.0045. This is the damping ratio. For the second case, when omega 2 is 15, we have eta 2 as 1 by 2, 0.02 by 15 plus 15 into 0.001. This will give 1 by 2, 0.00133 plus 0.015, which turns out to be 0.008166. Now, if you look over here, the damping value is more when the frequency is more. Omega 2 is more than omega 1. For omega 1, the damping value was 0.0045. For omega 2 15, the damping value is 0.008166. So if you look over here closely, the omega 2 is more for more omega 2, the eta 2 is also more, isn't it? However, if you look into the equation, this should be eta 1. However, if you look into the equation here, we have that eta I depends on both 1 by omega I and omega I. So that optimum value is always there. Alpha by omega I, what does that? The more the value of omega I, this component becomes smaller and smaller. And beta into omega I is that the more the omega I, this element is going to be more and more. So it is basically the summation of these two values. Now it will depend upon the value of alpha and the value of beta, that which one is going to dominate, and at the end what is going to give us a like for example in this case with omega 2 increasing, we got more value of the eta, right? So yeah, I hope this is clear. So we had 7 questions today, and I've taken the questions such that it will be helpful for you to solve in the assignment problem. And so with this, this is the end of the week 10 live session, and we have only 2 live sessions left. After that, I'll be taking an extra session in I guess, around 15th, 14th or 15th. 15th, I guess. 14th already have a live session. Tuesday. So 15th, first half, I'll be taking an extra session wherein I will go through whatever I have discussed till now briefly. And then if you people have any questions I see that because of the timing and the day, anyone, not even a single person is here to attend the live session. So just in case you're watching this video, on Wednesday, I guess 15th, I'll be having a live session, extra session, where if you have any kind of a doubts, any kind of a suggestion if you want, and everything, you can just come in that live session so that we can discuss, and then we will conclude the live sessions. Okay, so for now, this is it, and I'll end the live session now. Thank you so much.